Hey everybody. Today we're proving some theorems about probability functions. If you're taking a course in mathematical probability, you're going to be seeing and probably having to do a bunch of proofs. So it's good to start building some comfort and some skill with mathematical proofs about probability functions right from the start. As a reminder, a probability function is just a function that is defined on the sample space of a probability experiment, and for every event contained in that sample space, it's going to assign a number. And that assignment has to be done according to three fundamental axioms. The probability of S is 1. In other words, the probability of some outcome in the sample space happening is 100%. For any event in the sample space, the probability of the event is greater than or equal to 0. And if you have two disjoint events, two events with no outcomes in common, then the probabilities add. The probability of E1 or E2 is the probability of E1 plus the probability of E2. So a lot of important facts about probability functions can be proved right away from this definition, including some that just seem obvious. For instance, if E prime is the complement of an event E, then the probability of E prime is 1 minus the probability of E. So I recommend pausing the video before I show any of these proofs and trying them on your own. The key observation here is that the sample space can always be broken down into a disjoint union of E and E prime. So E union E prime is S, and E intersect E prime is the empty set, regardless of what E is. So we know the probability of S is 1 by property 1. We write S as E union E prime, and then since E and E prime are disjoint, we can break up that probability as the probability of E plus the probability of E prime. Then we just subtract probability of E from both sides, and we get the theorem. Second, the probability of the empty set is 0. So again, give this one a try really quickly. This proof is very short. The empty set is the complement of the sample space. So we compute the probability of the empty set by doing 1 minus the probability of S, just using the property from the first theorem we proved. We get 1 minus 1, which is 0. Next, if E and F are events where E is contained in F, so as sets, E is a subset of F, then the probability of E is no greater than the probability of F. I think a Venn diagram helps here, since we're talking about sets that have a relationship between them. Our approach is going to be to break up the larger set F into two parts. The one is just going to be E, which lies inside of F, and the other is going to be the rest, so F intersect with E complement. And notice that E and F intersect E prime are disjoint, so we're going to be able to apply the third property of our probability functions. A bit more specifically, we are going to say that the probability of F is equal to the probability of E plus the probability of F intersect E prime. Now by property 2, that last probability there, probability of F intersect E prime, has to be greater than or equal to 0. Therefore the probability of F is greater than or equal to the probability of E, which is what we are trying to show. Also notice, by the way, that equality here is going to hold exactly when F intersect E is the empty set. So the probability of F intersect E prime is 0. In other words, this can only happen if E and F are exactly the same set. Another quick one. For any event E, the probability of E is less than or equal to 1. So the key observation here is that E is a subset of the sample space, which has probability of 1. And therefore, we can use that last theorem that we just proved, probability of E less than or equal to the probability of S, therefore probability of E less than or equal to 1. Finally, for any two events, E and F, the probability of E or F, E union F, is the probability of E plus the probability of F minus the probability of E intersect F. This is known as the addition rule. The proof's a little bit more involved, so definitely pause the video here and give it a try using some of the techniques we've used up till now in this vid. One way to prove this is to break up that union, E union F, into E, and then the part of the union that's not in E. So that would be E complement intersect F. And since those two pieces are disjoint, E and E complement intersect F, we can just apply property 3 of the probability functions. So the probability of E union F is equal to the probability of E plus the probability of E complement intersect F. We have to deal with the probability of E complement intersect F. And I'm going to do this by breaking up the set F into the part that's in E and the part that's not. And so that's the set equality that you see in the upper right of this slide. F equals E intersect F union E complement intersect F. Once again, that union is disjoint. E intersect F and E complement intersect F do not overlap. So if we apply property 3 of probability functions to that equation in the upper right, we get that the probability of F is the probability of E intersect F plus the probability of E prime intersect F. And if we rearrange that a little bit, we can get the probability of E complement intersect F equals the probability of F minus the probability of E intersect F. So plugging all that into the equation at the bottom, we get the result. The probability of the union is equal to the individual probabilities minus the probability of the intersection.